Hi everyone. In this video, I will go through an example in which we have for sensitivity analysis, and in order to check the stability of the closed loop system, given that we have different process and different controllers. For this example, we need to consider this configuration as our standard closed loop system configuration, in which for GC the plant or process is determined by GP1 or GP2, and the controller GC is determined by GC1 or GC2. And for all the four combinations that we may have with GP and GCs, we need to find the sensitivity function S, the T and Q transfer functions, and study the input-output stability or BIBO stability. So we can start by forming our configurations. For the first one, I will assume that GP is GP1, which is 10 over 1 plus S, and GC, the controller, is GC1, which is 1 plus S over S. Then for the second case, GP will be still GP1, which is 10 over 1 plus S, but this time GC will be equal to GC2, which is minus 5 times 1 plus S over S. For case 3, GP will be GP2, which is 1 over 1 minus S, and GC will be equal to GC1, which is 1 plus S over S. And finally, for the case number 4, GP will be equal to GP2, 1 over 1 minus S, and GC will be GC2, which is minus 5, 1 plus S over S. So these are our 4 cases that may happen. I will start from the first case. So in the first case, I need to find out S, the sensitivity function, which is 1 over 1 plus Ls. And in this case, L is equal to GP times GC, which will result in 10 over 1 plus S times 1 plus S over S. And this will give us 10 times 1 plus S over S times 1 plus S. And if you just simplify it, we will end up with 10 over S for our Ls. So in the first case, Ls will be equal to 10 over S. Now for S, for the sensitivity function, we will have 1 over 1 plus 10 over S, which will result in S over S plus 10. So this is what we get for the sensitivity function S of S. Then for T, we have L over 1 plus L, the loop transfer function, divided by 1 plus loop transfer function, and we will get 10 over S over 1 plus 10 over S, which will result in 10 over S plus 10. So therefore, T is equal to 10 divided by S plus 10. And for Q, we have GC over 1 plus L. So for the first case, GC is 1 plus S over S. We will have 1 plus S over S divided by 1 plus 10 over S. And this will result in 1 plus S over S plus 10. So Q in this case will be equal to 1 plus S over S plus 10. And referring to all these three transfer functions that we have, we can see that the poles of the system, the poles of the closed loop system are located at S equal to minus 10, and therefore our closed loop system, the system is BIBO stable. So this is for the first case. Now we need to do the same thing for the case number 2, 3, and 4. I will do it here. So this is for case 1. Now for case 2, we have GP equal to 10 over 1 plus S and GC equal to minus 5 times 1 plus S over S. So let's start to form the sensitivity function 1 over 1 plus L, where L is 10 over 1 plus S times minus 5 1 plus S over S, and it's equal to minus 50 over S. After simplification, so S will be equal to 1 over 1 minus this is minus 50 over S, which will result in S over S minus 50. So S will be equal to S over S minus 50. Now for T is given as L over 1 plus L, and this will result in minus 50 over S, 1 minus 50 over S, which will result in minus 50 over S minus 50. So T is given as minus 50 over S minus 50. And Q is given as GC over 1 plus LS. So GC here is minus 5 times 1 plus S over S, and L is minus 50 over S. So after simplification, we will get minus 5 times 1 plus S over S minus 50. So I will write it again here. Q is equal to minus 5 times 1 plus S over S minus 50. And now again, having a look at these three transfer functions that we have, we can say that poles of closed loop system are located at s equal to 50, which means that the system, the closed loop system, is not BIBO stable. So this is the conclusion that we have for this case. So with this plant 10 over 1 plus s that we have, and we see that it is already stable. So the plant itself is stable. It doesn't have any unstable pole. But by the introduction of this controller, which has one pole at the origin, we end up with an unstable closed loop system. So let's continue and go through the case number 3 and 4 as well. In case number 3, we have GP equal to 1 over 1 minus S, in which we have an unstable system and the controller is 1 plus S over S. So I will write it again here. For case number 3, GP is given as 1 over 1 minus S, 1 over 1 minus S, and GC is provided as 1 plus S over S, 1 plus S over S. Now I can form again the sensitivity function, as we already have seen it here. Sensitivity function is 1 over 1 plus L, T is L over 1 plus L, and Q is GC over 1 plus L. So here we have 1 over 1 plus L, in which L is given as 1 over 1 minus S times 1 plus S over S, which will result in 1 plus S over S times 1 minus S. And using this L, replacing it here for S, we will get 1 over 1 plus S, S times 1 minus S. And from here we can have S times 1 minus S, S times 1 minus S plus 1 plus S for our sensitivity function. So we have S times 1 plus S at the numerator, and at the denominator we have so we will have S minus S squared plus 1 plus S, which after simplification will provide us minus S2 plus 2S plus 1. Now we need to determine the location of the poles of the system, or the roots of the denominator, in order to determine the stability of the system. So what we need to do is to set denominator equal to 0, or in other words, we will have S2 minus 2S minus 1 equal to 0, and find the roots of this polynomial. So it should be quite straightforward. So from here, S1 and 2, or P1 and 2 will be given as minus B, which is 2, plus minus square root of delta over 2A. And delta is B2 minus 4AC, where B is equal to minus 2, so B2 will be equal to 4 minus 4 times A is 1 and C is minus 1. So delta is equal to 4 plus 4, which is 8. So here we will have 2 plus minus square root of 8 over 2, which will result in 2 plus minus 2 square root of 2 over 2, and is 1 plus minus square root of 2. So what does it mean? So here we have t1 and 2, and the square root of 2 is square root of 2 is on 1.41. So from here we will have t1 equal to 2.41 and t2 equal to minus 0.41, which means that we have an unstable closed loop for the system. So our system is BIBO unstable. This is for the third case. By having a look at the sensitivity function, we can also calculate the T of S for this case, and then Q of S. So for T, we know that we have L over 1 plus L, where L is given here. So T will be provided for us as 1 plus S over S times 1 minus S over 1 plus S over S times 1 minus S. And if we simplify it, we will get 1 plus S over S times 1 minus S plus 1 plus S. And if we simplify it further, we will get 1 plus S over minus S squared plus 2S plus 1, which will provide us the same roots for the denominator, or the same closed loop pose. We can also go forward and find the Q, which is GC over 1 plus LS. So here GC is equal to 1 plus S over S. We have 1 plus S over S, and as the denominator we have 1 plus L, which is 1 plus S times 1 minus S. So if we simplify it, we will have 1 plus S times 1 minus S, and S times 1 minus S plus 1 plus S at the denominator. So Q will be 1 plus S 1 minus S over minus S squared plus 2S plus 2, again giving us the same pose of the closed loop system. Okay, so this is for case number 3, and we see that our closed loop system is unstable. If we have a second look at our case number 3, we see that our initial plant was unstable because we had the pole at S equal to 1. So with this controller, we couldn't make our unstable system stable in the closed loop. So now let's have a look at the case number 4, or the last case, in which we have GP given as 1 over 1 minus S and GC given as minus 5 times 1 plus S over S. From here, we can see that L, which is equal to GC times GP, is given as 1 over 1 minus S times minus 5 1 plus S over S. After simplification, we will have minus 5 times 1 plus S over S times 1 minus S for the loop transfer function of LS. Now I can form the sensitivity function S, which is 1 over 1 plus LS, and this will result in 1 over 1 plus minus 5 times 1 plus S over S times 1 minus S. And after simplification, we will have S times 1 minus S at the numerator, and S times 1 minus S minus 5 times 1 plus S at the denominator. Simplifying it further will result in s times 1 minus s, and at the denominator we will have minus s squared plus s minus 5 minus 5s, which will give us s times 1 minus s, and at the denominator we will have minus s2 minus 4s minus 5, or in other terms we will have s times s minus 1, multiplying the numerator and denominator by a negative sign, s2 plus 4s plus 5 at the denominator. So this is our s sensitivity function, and we can similarly find out the t, which is L over 1 plus L. Replacing L from here, we will have minus 5 times 1 plus S over S times 1 minus S, and the same thing here, S times 1 minus S will result in minus 5 times 1 plus S at the numerator, and S times 1 minus S minus 5 times 1 plus S. And if we simplify it further, we will get 5 times 1 plus S over S2 plus 4S plus 5. So this is T, and the last thing is finding out the Q, which is GC over 1 plus L. So in this case, GC is given as minus 5 times 1 plus S over S. So I will have here minus 5 times 1 plus S over S, and at the denominator we will have 1 plus LS, which is this guy here. So LS is minus 5 times 1 plus S over S times 1 minus S. And if we simplify it, let's see what we will get. We will have minus 5 times 1 plus S times 1 minus S, and at the denominator we will have S times 1 minus S minus 5 times 1 plus S. And simplifying it further, yes, we will get again S squared plus 4S plus 5 at the denominator, and at the numerator we will have 5 times 1 plus S times 1 minus S. Now, in order to check the stability of this system, we just need to find out the roots of the denominator, and denominator for all these transfer functions are the same. So we need to set S2 plus 4S plus 5 equal to 0, and from here S1 and 2 or P1 and 2 are provided for us. It's quite straightforward to calculate. You can refer to the formula for finding the roots, or maybe you can, let's do it like in the straightforward way. So we will have minus b plus minus square root of delta over 2a, where delta is b squared 16 minus 4 times ac times 1 times 5, which will result in 16 minus 20, that's minus 4. So replacing minus 4 instead of delta, we will have p1 and 2 equal to minus 4 plus minus square root of minus 4 over 2. And if you find out the roots, we will have minus 2 plus minus j. And here you can see that both of the poles are on the left hand side, so they are somewhere here. and our closed loop system is BIBO stable. We have a BIBO stable system. So having a look here, we can see that our open loop system or our plant is unstable because we have an unstable pole here. But by introducing this controller, we make our closed loop system stable. So using these 4 cases, you can see that if we have a stable system, we can keep it stable by introducing a proper controller, or we can make it unstable by introducing a kind of bad controller. And at the same time, if our original plant is unstable, by introducing a nice controller like this, we can make it stable, or we can keep it unstable if we don't design our controller properly. All right, that's the end of this video. I hope you would have enjoyed this, and it would be useful for you to understand how the feedback system, how the closed loop feedback system works in terms of the stability analysis. Thanks for watching, and see you next time.